Okay, we're going to continue here with evidence for global warming. The video that I was previously doing got cut off by mistake a little early. So after we looked at the information about the Keeling curve, it got cut off. So I apologize for that. So this is the second part of this. So if you saw in the video there was a seasonal fluctuation in the amount of carbon in the atmosphere, and there's reasons for this, okay? So there's a seasonal fluctuation because of vegetation. So most of this is in the northern hemisphere, and overall there's a huge decrease in the spring and the summer of CO2 because of the plants leafing out, and then the plants are doing photosynthesis and they're taking in all that CO2. So that's kind of why there's a seasonal fluctuation there. Now, why is there a latitudinal difference? There is a latitudinal difference. So 90% of the world's population lives in the northern hemisphere. 67% of the world's land is in the northern hemisphere. And so we have a lot of people and we have a lot of land in the north, and therefore that's going to lead to more CO2 and more warming in the northern hemisphere. However, there is a caveat here. Phytoplankton, which live all over the ocean, are single-celled algae, and they produce greater than 40% of the world's oxygen. So that is a little bit of a difference there. Okay, so why does it increase overall? Why does the CO2 increase? It's because of increased emissions from fossil fuel combustion and also net destruction of vegetation. So these are areas on the globe with increasing CO2 concentrations. Now, in 2009, developing countries overtook developed countries in CO2 emissions. Think about this demographic transition. Might give you a clue as to why that's happening. So if we take a look at this, industrialization happens first. When that happens, fossil fuel combustion goes up in stage 2. So in stage 2 here, you're getting industrialization and the fossil fuel combustion is going up. But in stage 2, there's really not the political will or the money to pass progressive environmental laws until later, stage 3 or 4. So a lot of times these countries that are just developing and just getting industrialized are like, hey, we now have the technology to use coal and oil and natural gas and all these things. We can provide electricity for our people. We're really excited about this. And they're not yet there with trying to limit that stuff. So it's hard for us to tell them what to do because we were once there ourselves. Now, this is the second piece of evidence for climate change, for global warming, is that the temperature is actually going up. So global temperatures have increased on average 1.4 degrees Fahrenheit, but regionally up to 4 degrees. So there's a big deal here with breaking the 1 degree Celsius barrier. We don't want to raise the temperature, average temperature of the globe all that much. And if we break that 1 degree barrier, it's really kind of a big deal. So this is a graph here showing 1850 to 2015, and you can see the temperature going up, and we have broken here that 1 degree barrier. So the first 9 months of 2015 show average global temperature has hit 101.2 degrees Celsius higher than normal, halfway to the dangerous threshold of 2. So we think that if the temperature raises 2 degrees on average all the way around the globe, it's going to cause a whole lot of problems. So we do not want to get there. So temperature is going up. This shows you mean temperatures from 1999 to 2008. You can see the darker colors are the higher temperatures. And you can see that that has caused ice to melt. So 45% of the northern ice caps have melted. This is 1979, and on the right you have 2007. You can see this big section down here is now missing because it has melted. So temperature rising causes ice caps to melt. Another piece of evidence here is changing species composition. So what does this mean? This means that if it gets warmer, where different organisms are located and can live changes. So you see a current map here. And then this current map is of Michigan and Wisconsin and Minnesota and Iowa, Illinois, Indiana, Ohio, and Missouri. Nice variety of species of trees here in the forest. Up way in the north here towards Canada, you've got spruce and fir, white, red, and jack pine, aspens, birches, things that you would think of normally in a colder place or more in a higher elevation place, and they live up here. If we have lower emissions, well, we've lost a little bit of diversity here. But look what happens when we have higher emissions, which means that we have higher CO2 and higher greenhouse gases and more warming. So the warming is going to knock out some of the diversity of the species here, and no longer can that spruce and fir and aspen and birch live up here. And now we've got all the same kind of trees, oak and hickory, oak and pine, elm and ash and cottonwood. It's much less diverse. So this is changing species. You can also see this in birds. So this is a map here that shows you where do certain birds spend the winter. The lighter blue is 1966 to 67, and the darker blue is 2005 to 6. So let's take one example here, the ring-billed gull. That's a seagull. You can see them on the beaches of North Carolina if you go there. The ring-billed gull, you would think, would want a warmer place to live since he is a seagull. Used to spend the wintertime in the south of Louisiana and Alabama, Mississippi, not Alabama. And then now look where he's spending the winter in 2005 and 2006, way up here in Tennessee and Kentucky, which used to be way too cold for this bird in the wintertime. And so guess what? It's getting warmer. So this is a piece of evidence of global warming because our birds are spending their winters in different places because it's now warmer. Okay, and then we have proxy data. What is proxy data? Proxy data is physical preserved characteristics of the environment they can stand in for direct measurement. So what does that mean? I wasn't there to measure what was in glacial ice 10,000 years ago, but I can take a core out of that ice and I can look at it and I can see what's there. Same thing with sediments and tree rings and coral reef bands. I can take a look and the bands will show me the ages of those organisms, and it will also show me things about how they grew and what was present in the past. So we call that proxy data. Here's an interesting little creature called a foraminifera. Different species prefer different temps, and they have a very narrow range of temperature tolerance, and they fossilize really well. So when these guys make fossils, they lay down themselves on the layers of the ocean floor, and if we pick up some of those ocean floor layers and take a look for fossils, we will see different species that were there laid down in different temperatures. So it will help us figure out what was the temperature of the ocean at different times in the past when we were not actually there, which is kind of interesting. Now we're going to take a look at ice cores. What do ice cores tell us about climate change? And this is where you can take a large piece of ice out that is very, very thick and that has been there a long time, and we can see what kind of gases are in the ice. It tells us about the atmosphere.
My name's Nerily Abram. I'm an ice core scientist and I work with the British Antarctic Survey. And the reason that I work on ice cores is that they're an amazing way of going back and looking at what the Earth's climate was like in the past. And that gives us information on how the Earth's climate is changing now and how it might change in the future. When you get to a field site in Antarctica, there's nothing there. The people who go to Antarctica and do these sorts of jobs are scientists, but once you get into the field, you're pretty much everything. So you need to build your camp, you become a carpenter, you become an electrical engineer, you're a cook. You have to be able to be very self-sufficient to make the project a success. The drill works on a winch. So when we lower the drill down, we drill about 1.5 meters of ice, and then we bring that to the surface, and we lower the drill back down again and drill the next 1.5 meters of ice. And we keep on repeating that process over and over again until we reach the bottom of the ice sheet. When we drill down through the ice sheet, we're drilling further and further back in time. We drilled an ice core that was 364 meters long, and the ice that we recovered from the bottom of that ice core is over 20,000 years old. This is a part of Antarctica where climate is changing really quickly at the moment, and the temperature has warmed by over 2 degrees in the last 50 years. We're seeing glaciers flowing faster than they have in the past, ice shelves are collapsing. When we cut open the ice, we can see these bubbles of ancient atmosphere that have been trapped inside the ice ever since it formed over Antarctica. And we can actually measure the composition of that ancient atmosphere, and it's through measuring the greenhouse gases from the bubbles in ice cores that we get this clearest link between what the temperature of the Earth has been like in the past and the concentration of greenhouse gases in the atmosphere. And that allows us to have a better understanding of how the climate is changing now and how it might continue to change in the future.
You can see there what they do when they measure ice cores. So let's take a look at another short little video here about a National Ice Core Lab storage place and what they do.
It's a busy, freezing cold day inside the National Ice Core Lab in Denver, Colorado.
You're going to cut gas samples out of this core.
Scientists from Maine to California here to cut pieces of precious Antarctic glacier ice to take back to their labs for study.
We started the Ice Core project in 2005.
With support from the National Science Foundation for a project called the West Antarctic Ice Sheet, or WAIS Divide, lab manager Mark Twickler and a team of scientists, engineers, and support personnel traveled to the bottom of the world to drill out and bring back these ice cores. The goal of the project? To collect and study perfectly preserved records of the distant past.
The unique things about polar glaciers is each year that it snows there, the snow never melts. So you get 1 year of snow on top of the next year's snow. It compresses, so everything that fell out of the atmosphere, dust, salt from the ocean, volcanic ash, is preserved in that ice core.
This particular ice sheet is more than 70,000 years old. The team drilled down more than 2 miles into it to retrieve these cores, which were then flown to the U.S. and stored in a giant 40 below zero freezer here at the Ice Core Lab.
Inside this freezer contains more than 10 miles of ice cores collected from around the world.
Twickler says the ice core's layers are like tree rings, each layer representing a year of weather and snow.
We can tell what the temperatures were. We can tell how rough the oceans were around Antarctica. We can tell how dusty Australia was.
Scientists are keen to study the bubbles trapped in the cores, each a tiny pocket of air frozen in time.
We can measure a variety of gases that were in the atmosphere at the time the bubbles were formed.
Other scientists want to know how ice sheets melt over time.
We don't necessarily have a really good handle on how the ice sheet as a whole will respond in a case of changing climate.
Twickler says this icy blast from the past is helping researchers better understand the mechanics of climate change, and that in turn will help them make better predictions as to what a changing climate may mean for our future. For Science Nation, I'm Miles O'Brien.
So that's really interesting to take a look at the ice cores, because now this gives us a really good piece of evidence of what the future of what the atmosphere was like in the past. And that way we can tell what the difference is between now and thousands of years ago. Okay, so let's take a closer look at these ice cores. We've got data from 500,000 years. We look at air bubbles trapped as each year of ice is laid down. Ice in warmer temperatures has more oxygen 18 isotope, which is heavier. And so for 500,000 years, CO2 has never been above 300 parts per million. And we know this from the ice core data. The last 60 years, it's risen to over 400 parts per million. So we know definitely it's going up very quickly. And methane and nitrous oxide has also increased over time. And we have learned this from the ice core. Okay, other proxy data we could look at: tree rings, coral growth rings, shows you how the corals grew in different years. And pollen spores, we can tell from the past kind of fossilized pollen spores, we can see what the differences are. And this tells you how many years and when we can look at some of this data. So we have tree ring data for a large amount of area. We have ice core data. We have lake sediment, coral reef, ocean sediment, and continental coastal sediments. So this shows you how many years we have of records for all of these different pieces of data. And so what we can do is look at what happened in the past by measuring certain things from all of this data that can give us a clue as to what went on before we were here to record it, which is kind of interesting because then we know what we're looking at for the future. So what really caused carbon dioxide temperatures to shift before humans were around? Because there were shifts. The path of orbit and the position relative to the sun caused a little bit of change. And also, orbital tilt caused a little bit of change. Not a lot, but a little bit of change. So there are natural fluctuations. So here's our null hypothesis. An increase in solar radiation is causing global warming. Is that true? Is just increase in solar radiation causing global warming? Is that what's happening to us? Well, no, because if this were the case, we would see a greater difference in the temperatures of summer and daylight and lower latitudes. We're not really seeing that. So if we were really getting more solar radiation, we'd see all kinds of temperature differences that aren't happening. So we know it's not really this, but you may have heard this. And so what do we do? How do we make predictions? We use climate models to make predictions. And so all kinds of scientists are out there making climate models. Here's a schematic for a global atmospheric model right here. These models look at air, ocean temperatures, concentrations of CO2 and all kinds of other greenhouse gases, amount of vegetation, amount of sea ice. Modeling is a very good way to look at what might happen in the future. There's a lot of this going on right now. So we've got some feedback loops for you to look at in your packet. So I'm going to go through these a little bit here, and you can pause the video and whenever you want and draw these. The first one says CO2 traps heat, which is a greenhouse gas. And then warmer temperatures mean the ocean cannot hold as much CO2 and the oceans release extra CO2. And then that CO2 traps heat and then it keeps going from there. So is that a positive feedback loop? Is it a negative feedback loop? You can draw it, you can decide. This is the second one. Snow and ice has a high albedo. That means it reflects a lot of light and it reflects it instead of absorbing it. As it melts, the dark land or water absorbs more heat, which melts more ice, which means it keeps going from there. So is that positive or negative? You can draw that one. Here's one. Higher temperatures lead to more soil decomposition by bacteria, which release more CO2 in the process. And then what happens next? See if you can figure that out. Tundra permafrost thaws, develops anoxic standing water. Anoxic doesn't have oxygen. Anaerobic decomposition releases more methane. Okay? And what does the methane do? It causes warming, which causes more permafrost to melt. So draw that feedback loop. Here's a negative one. CO2 stimulates plant growth. Plants uptake CO2 through photosynthesis. More heat, more evaporation. Water vapor is a greenhouse gas, but soon clouds form which shield and cool, and the positive feedback becomes a negative feedback. So see if you can draw those in your packet in the little boxes where it says feedback loops. And that's it. That is part one of global warming, evidence for global warming. And then we will continue with part two, which will be the effects of climate change.